Hi dear students, we are coming to the last lecture of our topic, which is the particle and wave character of electrons. Einstein had suggested in 1905 that light has a dual character, as wave and also as particle. In 1923, de Broglie proposed that matter also has a dual character, as wave and as particle. 3 years later, in 1927, de Broglie's idea was confirmed by experiments and he received the Nobel Prize for his discovery of the wave nature of electrons in 1929. This made him the first person to receive a Nobel Prize on a PhD thesis. De Broglie derived an expression for calculating the wavelength associated with the motion of a particle of mass m moving with velocity u, according to which lambda equal to h by mu, where h is the Planck's constant. The de Broglie's equation for the wave character of electron can be easily derived by using Einstein's mass-energy relationship, which is E equal to mc square. Equating this energy with the energy of photon, that is E equal to h nu, we have h nu equal to mc square. As nu equal to c by lambda, we can write it as hc by lambda equal to mc square, where from that lambda equal to h by mc. Replacing c by the velocity u of the particle, we have lambda equal to h by mu or h by p, where p is the momentum of the particle, this equation is known as de Broglie equation. With this new discovery, de Broglie opened the gateway to the development of wave and quantum mechanics in the early 19th century. The de Broglie's concept about dual character of matter is significant only for microscopic particles. It loses its importance when applied to macroscopic bodies. This is because the wavelength of matter waves associated with macroscopic bodies are too small since they have higher mass. Therefore, we can say that macroscopic bodies have no de Broglie wavelengths. Next, we have to discuss the Heisenberg uncertainty principle. It is articulated by Werner Heisenberg in 1927. According to this principle, it is not possible to determine precisely both the position and the momentum of a moving particle. This principle is mathematically expressed as delta x into delta p greater than or equal to h by 4 pi, where delta x is the uncertainty with regard to the position, delta p is uncertainty with regard to the momentum of the particle, and h by 4 pi always it's a very small value. The significance of this equation is that if delta x is very small, that is the position of the particle is known more or less exactly, delta P would be very large. That is, uncertainty with regard to momentum will be large. Similarly, if an attempt is made to measure exactly the velocity or momentum of the particle, the uncertainty with regard to position will become large. The physical concept of the uncertainty principle may become clear when it is realized that all observations have to be made by impact of light or photons. If the object is of reasonable size, its position or velocity will not be altered by the impact of light. Hence, the uncertainty delta x or delta p would be negligible. But this cannot so when the object is extremely minute, such as an electron moving in a circular path. It will suffer a change in its velocity and path due to the impact of even a single photon of light used to observe it. By this principle, it is not possible to know exactly the position of an electron moving with a particular velocity as it is implied by Bohr's model. Instead, it is possible only to predict the probability of locating an electron moving with a particular velocity in a given region of space around the nucleus at a given time. Thus, for the energy of matter, we can have both the equations, but it purely depends on the size. If the particle is large, its particle property will be observable, and we can use the equation, Einstein's equation is equal to mc square. But for a small particle like photon, it mainly behaves express its wave-like property, and for them we can use equal to h nu. But for an intermediate particle like electron, it can have both the particle property and wave property, depends on situations. That is, everyday life follows classical mechanics, where we can ignore the Planck's constant. But at atomic and subatomic scales, quantum effects are dominant and must be considered. Niels Bohr and Werner Heisenberg were the architect of this quantum worldview, along with Planck, Einstein, de Broglie, Schrödinger, Pauli, and Dirac. Now I hope you can differentiate particle properties and wave properties. But our quantum world is at odds with our common sense view of physical objects, and we may feel some confusion in defining uniquely what is a particle and what is a wave. Students, by this I am concluding my chapter. Thank you and bye-bye from this semester also. You should have an assignment and a test based on this chapter. Keep study well. All the best, dears.